Yeah, go check out this tool. I'm not sure how big your eyes are. And then you can adjust the darkness threshold. It will find the darkest bit in the eye, which meant to be your pupil. Not always, but most of the time. Because I think everyone's pupil is black, regardless of the color of the eyes. But yes, depending on the eye, on the light conditions and things like that, this might need tuning. I'll jump straight into development. So we're doing something different today. Yes, obviously we're using this all new GPT-4. Oh, for not is a better name, isn't it? For not to use it. Yeah, I'm trying to detect the abnormalities in images. We're primarily, so eventually we're gearing towards finding misconduct. So yeah, big task, but yeah, there's a lot of images that are to do with fraud in scientific literature. So I have a whole list here of fraud conducted in scientific literature. Yeah, names, blame and shame. We won't focus on the names. We're just looking for some of these image examples. So supposedly this EG, but I couldn't find. Wait, that's oncology. A background is it's oncology or EG? Yeah, it's hallucinating a bit. Is that link working? No. Yeah, it's just making up links. Is it? Isn't it? That's not good. So yeah, ChatGPT-4 not. Did not fix the link problem. It is generating much faster though. That could be a good thing. Can you try browsing for any images in scientific literature that were from papers that later were retracted. Particularly of interest could be biology, so biological arrays. What is those gel arrays? Arrays. Oh, come on. Arrays. Oh, hopeless. So I need some of those example images because we are doing an image anomaly detection application, ideally in JavaScript. But I need the example image dataset. Let's see what it says. Well, it's still better than Googling. Saying search 5 sites, search nature. Yeah, I don't trust this search data far, but what? In the blocker who spotted problems in dozens of cancer papers. Okay, I don't know why it's focusing on nature, science. Okay, I'm after the images and some of this. Yeah, it's just making up. Yeah, this link doesn't work. That link doesn't exist. A copy link. Let's check it in a different window. No, doesn't exist. Normally the first one. Okay, that table does work. Strip is retracted. Yeah, behind a paywall. Paywall. Blah 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 blah. Yeah, I'm not interested because it doesn't have the images. Clear. I need a data set for relevant images. Yeah, so looking for images that were retracted from papers. I mean, when they retract, they normally just put the retract label. It's amazingly how this paper still gets cited even after retraction, but I'm after the actual images. Dun, 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 dun.
To find actual images that were retracted from scientific papers, you can access several databases and platforms that specifically focus on scientific misconduct and retractions. Here are some useful resources.
Yeah, Retraction Watch
1.
is
Retraction
quite,
Watch
useful.
database. Retraction Watch provides a comprehensive database of retracted papers and includes detailed information about the reasons for retraction. They sometimes include images that were part of the retracted studies. Retraction Watch database at retractionwatch.com/retracted-papers. 2. PubPeer. PubPeer allows researchers to comment on and review published papers. Discussions often include direct references to manipulated images, and users sometimes upload these images to highlight issues. PubPeer.pubPeer.com/. 3. PubMed Central, PMC. PubMed Central is a free archive of biomedical and life sciences journal literature. Even retracted papers are often available here, complete with the original figures and images. PubMed Central, pubmedcentral.ncbi.nlm.nih/PMC. 4. ResearchGate. ResearchGate hosts a variety of research outputs, including papers that have been retracted. You can often find the original images and figures within these documents. ResearchGate.researchgate.net. 5. Open Science Framework, OSF. OSF is an open access repository that includes datasets and research outputs. You can search for specific papers or datasets related to retracted studies. Open Science Framework //osf.io. 6. Zenodo. Zenodo is a repository for research outputs including images and datasets. Searching for retracted papers or specific authors can yield relevant images. 3. Use PubPeer for community insights. Check PubPeer for discussions on these papers. Users frequently highlight specific images and provide commentary on the manipulations. Here are some examples of high-profile retractions involving manipulated images.
Yeah, these are mainly cells, stem cells, stem cells, ideally after EEG, ECG. But, well, these fields are more popular for images. That was wrong link. It's not even a retracted paper. And it's funny, OpenAI, instead of fixing, what is it they're fixing, making the voice or whatever sound like the movie Her, they should have fixed how it's generating links. That would be way more useful. Okay, I can't actually find anything. Just go simply for Bing image search. Yeah, looking at that gel arrays images. Yeah, GPT is not really helping, is it? It's not really helping. Yeah, Bing search is hopeless. Scientific pair of images, biological arrays. Retracted images of biological arrays, gel. Okay, that's retracted. It's funny, the images, well, everything is still there, it just has the retracted thing all over it. Does it say why? Does it say why it was retracted? No confidence. Evidence of Photoshop manipulation. Okay, how do I? There should be more data. Yeah, you would expect there would be no data available in a paper like this. So which parts, what images were manipulated? Well, those are infographics. Is that the real image? I don't know. It would be really hard to find any manipulation in there. There's nothing obvious. It's something on chip. Well, right. So what was manipulated about it? I do not know. Specific examples of those. I've seen someone showing one of those examples of cell arrays that had like copy paste that I need an example of a cell array where there is an obvious manipulation of the image taken with parts being copy-pasted multiple times. Let's go for it as well. Search for images. Nah, can't find anything. Hopeless. It's hopeless. Retraction of cell array with obvious image manipulation to create false results. Is this a legit paper? Was it retracted? It's a different order. Keep making up stuff. That's not gonna go far, would it? Fraction may mention the figure where manipulation occurs. For instance, figure 4, image were copied and pasted multiple times to fabricate data. Okay, where is that? Is this the same order? No, it's not. And this paper was not retracted. Oh, come on. So I'm not sure what is it making up. Okay, there is something on Retraction Watch. Okay, Retracted article. Still has a DOI and everything. A retraction to this article was published on 2017. Yeah, it was cited 147 times. Figures available. Okay, yeah, that's the type of figure I was looking for. The bot said there was obvious manipulation figure for it's fine. Are they for real charging to allow access? That's just a notice. Figure 4, is it?
In this letter, some PCA input panels contain duplicated bands, figs 1b and 2a, and supplementary figs 4 and 6a. In fig 2e, the ARF promoter panel is a duplicate of the road panel in supplementary fig 8c. The raw data were not available to verify the data. Given these issues, the authors wish to retract the letter. The authors deeply regret these errors and apologize to the community. Peter Klatt, Sonia Delgado, Esther Conde, Fernando Lopez Rios, Montserrat Sanchez Cespedes, Juan Mendez, Francisco Antequera and Manuel Serrano agree with the retraction of the letter. Susana Gonzalez cannot be reached.
Okay, so figure 1. Yeah, on ResearchGate as well. It's Google Scholar. The paper can. Come on. Does it take forever? There's a PDF. Right. Okay. Yeah, and this one must have been published, placed much earlier, so people probably will be still citing the paper. This one doesn't. Yeah, this one doesn't mention retraction. Okay, so we are after this particular figure. Let's see if there's anything obvious about it to the naked eye. So I assume there is a duplication here and there. So they don't make it obvious. 1B. Duplicated bands in 1B, duplicated bands in 1B. So that would be this bit here. Would be still like copyright on it and stuff. It's just ridiculous how these things work. Export as PNG. It was the original JPEG. Let's do JPEG to HL array rod. Pop it in an image. Okay, so we already have some code for it. When we go check out bionichaos.com, there should be no fraud on it. And yes, ChatGPT was used and is used for generating these tools and blogs and things. So don't be surprised. Let's copy relative path. Let's do the clone business. A clone business. It's the second image that we have. Comment that one out. Let's run and see what we get. And we get, for some reason, not enough matches found. So there's no match. No match. Well, some probably were inverted. Again, this is where we are gonna use GPT. Let's close those. Yes, we have this code. We have this. Okay, so we have this code. We have this output attached as an image. But we know that this image has manipulation, has duplicate the areas.
The zero matches issue might be due to a variety of reasons, such as insufficient or poorly detected key points, overly strict matching criteria, or issues with homography calculation. To improve the code, let's address the following. Ensure enough key points are detected. Adjust the SIF parameters to ensure robust key point. Relax the matching criteria. Use a less strict ratio test and distance threshold. Review the homography filtering. Check if the homography filtering step is too strict and refine it. Here's an updated version of the code with these improvements. Increase key points. Increase the number of SIF features to 1500 for more robust key point detection. Relax matching criteria. Adjusted the ratio test to 0.8 and the distance constraint to 20 pixels. Match drawing. Ensured all good matches are drawn to visualize the matching process. Run this updated code to see if it improves the detection of clone regions in the image. If there are still issues, consider further tuning the parameters or using additional techniques like preprocessing the image to enhance key point detection.
Yeah, it's always getting reverting to a generic data path, image path. So normally just paste the code. Copy pasting is a skill, isn't it? And then getting rid of that. Yeah, that's the correct file. Let's run it again. Have to close this one for another to be open. Yeah, not enough matches. Not enough matches are found. And that's odd. There should be some. Might be not that obvious. Search this image. There's a lot of images. I was expecting something very similar with labels of how this image was manipulated exactly, but getting a lot of similar images, but not exactly the same. Is there an option if there's no image source? Well, yeah, because this one's from a PDF. Would expect something like this on Retraction Watch, where they actually show exactly the manipulated bit. So I might need to confirm. Might need to confirm that. Wait, did I forget to? Yes, so nothing is found, which is unusual. This image is from a retracted paper. Wait. This image is from a retracted paper. It should have duplicated areas in it. Now we're writing Python code that will detect those duplications. But we need to fix the code. Currently it's not finding anything. How to fix the code? Make sure you keep the image path intact. Yep. I'm sick and tired correcting it. It will revert to some default value every time.
To improve the clone detection process, let's revisit and refine the key components. We increase the number of key points, relax the matching criteria further, and ensure we draw enough matches to visualize potential duplications.
The other thing is that the duplications might be not just copy-pasted as they are. They might be mirrored or flipped. Yep.
Increase key points. Increase the number of SIF features to 2000 to ensure more robust key point detection. Further relax matching criteria. Adjusted the ratio test to 0.85 and reduced the minimum distance constraint to 10 pixels to capture more potential matches. Homography and RANSAC. Ensure the homography calculation is properly handled to filter outliers. Run this updated code and see if it captures the duplicate regions more effectively. If there are still issues, consider further parameter tuning or visualizing intermediate steps to understand where the process might be failed.
I don't see them as well. Like one of those games where you have to find the matching pairs. Yeah, and it will be other, yeah, so we can do also noise. We should be able to do other techniques to find the abnormalities in the image. One of them could be ELE, I forget what it stands for, but we can try other techniques as well.
Given that duplications might involve mirroring or flipping, we should include additional transformations to account for these scenarios. We use CV2, match template, which is well suited for such tasks, as it can handle various transformations. Here's how you can modify the approach.
Okay, this one's running for longer. Yeah, using one CPU at a time. I don't know why. That's not ideal. Yeah, before we were starting to optimize for multi-threaded multi-threading. Okay, this one had the detections. They're super weird. They're like false positives, false negatives. Essentially false. Yeah, I wonder what will it say if you just show this image. Obviously, it's an absolute mess.
Transformations included flipped and rotated versions of the image patches. Template matching, use CV2, match template for matching transform patches against the image. Thresholding, use the similarity threshold to filter out potential matches. Run this updated code to check if it detects the duplicate regions more effectively, even with mirroring or flipping transformations. Adjust the window underscore size, step underscore size, and threshold parameters as needed to optimize the detection process.
Yeah, we need to optimize those parameters. What do we need to optimize, or how do we fix the code? Yeah, this is obviously not great. Okay, what are we doing? Let's see, how do we improve it? I eventually want to turn it into a Flask application, so it's available on the website, and primarily relying on JavaScript.
The current output indicates a large number of false positives, making it difficult to discern meaningful duplicated regions. To improve the detection, we can increase the threshold, make the similarity threshold stricter to reduce false positives. Post-processing, apply clustering to the detected rectangles to mode overlapping detection. Display only strong matches, limit the displayed matches to the strongest ones. Let's implement these improvements. Step 1. Increase the similarity threshold. This will help filter out weaker matches. Step 2. Apply non-maximum suppression, NMS for mode overlapping rectangles into a single detection, which is helpful in reducing clutter from multiple nearby detections. Step 3. Display only strong matches. By displaying only the strongest matches, we can ensure that we are visualizing the most likely duplicated regions.
Didn't find, I don't know. So obviously there's nothing there, nothing here. No. Oops. Didn't find suggesting those these two or something. I mean, they do look similar, but yeah, the other thing that they have that shadow to them. I don't know. Yeah, you can't. It's really good. It's an fairly old paper. I can't find it with naked eye. I mean, someone who is looking at a lot of these images should. It looks like some extra lines here and there. This one is it detecting noise? How about the different technique? So we also have this different code. Could you explain the code? And we get this output for this specific image. Can we tell from it if the image was manipulated or not? Yep.
ELA is used to detect areas in an image that have been altered. This technique relies on the fact that recompressing a JPEG image causes changes in the compression artifacts. Areas that have been edited and resaved will exhibit different compression levels compared to unaltered areas.
Using this image shops, enhancing displaying result.
Analysis of the ELA image. Black areas indicate regions that have similar compression levels, meaning they're likely unaltered. Bright areas indicate regions with different compression levels, suggesting possible alterations. Code review and improvement. Your code is fundamentally correct for performing ELA. However, to make it more robust and improve visualization, let's refine the enhancement process and provide a better explanation of interpreting the ELA image. Original image provides context for the analysis. ELA image. Bright spots in the ELA image indicate potential areas of manipulation. These bright spots occur because the recompressed image has different compression artifacts compared to the original image. If a certain region stands out significantly, they might indicate that this region was edited or manipulated.
Okay, so this is what we currently have for the code. And this is the new one. Yeah, it's kind of the same.
By analyzing the ELA image, you can identify which parts of the image have potentially been manipulated based on the compression inconsistencies. Adjust the quality and scale parameters if needed to fine-tune the sensitivity of the ELA analysis.
And this is not overlaid, so it's hard to find which one's which. Yeah, 100, 150. Oh, that's just that corner there. Anyway, well, that's not very obvious, is it? I don't know, I'm still getting not obvious results. Can we improve the code, the current processing, or try a different technique to try and determine if this image was manipulated? Well, we kind of know it was because it's from a paper that was retracted.
The current ELA output may not be providing clear indications of manipulation, likely because ELA is more effective for detecting certain types of edits, e.g., splicing or blending, rather than subtle duplications or mirroring. Let's improve the ELA processing and explore an alternative technique, principal component analysis, PCA, on image patches.
Yeah, it's getting more and more complicated.
Improvements to ELA processing. Adjust quality and scale parameters. Fine-tuning these parameters can help highlight differences better. Contrast enhancement. Apply additional contrast enhancement to the ELA image to make the differences more visible.
Yeah, eventually we want the magic numbers to be controllable there, so you can there's a scale factor and quality. This one is not the scale is not even being used, is it? No, and that's what we get for the clone analysis. Yeah, takes some time to actually process.
PCA can help detect duplicated or manipulated regions by analyzing the variance in image patches.
Yeah, it takes some time, but no, it's not helpful. It's finding if there are false positives. So we can close that. It's an improved version for the ELA. I'm not sure what that means. It's a 300, 250, 300. Yeah, just showing those edges. Yeah, obviously they're duplicating because they look the same, but that's not what I'm after. That line there. Yeah, it would be those entire markers that were like swapped, duplicated. Something was done to them. Forget that my screen is smaller than what I'm showing. It goes up to about here. Anyway, this is not obvious. We need a different way of detecting manipulation in images. Suggesting PCA.
PCA for image manipulation detection. Extract patches. Divide the image into smaller patches. Apply PCA. Use PCA to reduce the dimensionality of these patches. Reconstruct patches. Reconstruct the patches from reduced components. Difference image. Compute the difference between the original and reconstructed patches to highlight manipulated regions.
I mean, to begin with, it looks slightly more useful. This is what I get from the PCA code result for this specific image. Can you explain what the result is, and how do we determine if the image was parts of the image were duplicated or not? Yep.
The PCA difference image shows the differences between the original image patches and reconstructed patches using PCA. Bright areas in the PCA difference image indicate regions where there are significant differences, which could suggest potential manipulations. Explanation of the PCA difference image. Original image. The original image is displayed on the left for reference. PCA difference image. The right image shows the absolute differences between the original and the PCA reconstructed patches. Bright spots in this image highlight areas that deviate from the expected reconstruction, which can indicate possible manipulations. Interpreting the results. Bright areas indicate regions with high reconstruction error, suggesting potential manipulations. Dark areas indicate regions with low reconstruction error, suggesting these areas are more consistent with the rest of the image. Next steps for verification. Manual inspection. Visually inspect the bright areas in the PCA difference image. If these regions correspond to expected duplicate regions or irregular patterns in the original image, they might indicate manipulation. Combine with other techniques. Use ELA or other forensic analysis techniques to corroborate findings. Refining the detection, patch size and PCA components. Experiment with different patch sizes and the number of PCA components to see if the detection improves. Thresholding. Apply a threshold for PCA difference image to highlight only the most significant differences.
I don't know, can you see it? So my expectation would be that if we get this white spot there, does it mean that this marker was essentially copy-pasted from somewhere else in the image?
Here's a refined approach with thresholding. Explanation of refinements. Thresholding. Apply a threshold for PCA difference image to highlight significant differences. This helps in isolating areas that are most likely manipulated. Patch size and components. Adjust these parameters based on the image to improve detection accuracy. By running this refined code, you should get a clearer visualization of the manipulated region. Adjust the patch underscore size, and underscore components, and threshold parameters to optimize detection for your specific image.
Yeah, this type of errors with the code should be simple. There's some sort of a typo. So if I select the whole thing and use the GitHub Copilot, start a new chat, pop that error in, let's see what it says. Indicates mismatch, dimension, yes, in your case, there's likely in regroup a reconstructed image. Oops. Yeah, did we forget something? Okay, the code is running. And now more white regions in it. I don't know what to make of it. It's the original one, the current one. Yeah, it's essentially just changing like the contrast. Still not very obvious, I would say. Well, because for example, this bit here, I can't actually see it anywhere else. You'd expect that to be the case. But essentially this is where a PCA component analysis indicated where this image was manipulated. So, and I think the original paper was manipulated. The original image in the paper was manipulated in other figures as well, so we could check those out. This one is not entirely obvious, so they did a really good job. But yeah, let me know what you think. And if you've seen any other images that I could use. Can you explain the PCA analysis again in relation to this image? What would a white area on the PCA different image mean exactly? Does it, for example, mean that that area was copy-pasted from another region within the same image, or something else was altered?
Chap explanation of PCA difference image. In the PCA difference image, white or bright areas. These regions indicate a high reconstruction error. This means that the patches in these areas differ significantly from the expected pattern based on the overall image. Such differences can be due to manipulations like duplications, splicing, or other alterations. Black or dark areas. These regions have a low reconstruction error, indicating that the patches in these areas are consistent with the overall image pattern and are less likely to have been manipulated. PCA analysis in relation to this image. 1. Patch extraction. The image is divided into smaller patches. Each patch is then analyzed to see how well it fits into the overall pattern of the image. 2. Dimensionality reduction. PCA reduces the dimensionality of the data while retaining most of the variance. This means it keeps the most significant features that describe the image patches. 3. Reconstruction. Each patch is then reconstructed using the principal components. 4. Difference calculation. The difference between the original and reconstructed patches is calculated. Areas with a high difference are highlighted in the PCA difference image. Interpretation of the white areas. High reconstruction error. Bright areas in the PCA difference image indicate regions where the original patches differ significantly from the reconstructed patches. This could be due to copy pasting. If a region has been duplicated from another part of the image, it might not fit well with the surrounding patches, leading to a high reconstruction error. Splicing. If parts of the image have been spliced from different sources or manipulated, they might also stand out in the PCA difference image. Other alterations. Any other significant alterations to the image, such as heavy retouching or editing, can also result in bright areas. Steps to further verify manipulations. 1. Visual inspection. Manually inspect the highlighted areas in the PCA difference image against the original image to see if they correspond to expected manipulations. 2. Combine techniques. Use other forensic techniques such as ELA, noise analysis, or deep learning-based methods to corroborate findings. 3. Compare with original figures. If you have access to the original figures or images from the paper, compare them with the manipulated image to spot differences. Example code to highlight white areas. Here's a small enhancement to threshold and highlight the white areas in the PCA difference image. Python import CV2, import numpy as np from sclearn.decomposition, import PCA, import matplotlib.pyplot as plt. Def extract patches image patch size. Patches equals h equals image.shape for I in range 0, h patch size plus 1 patch size for j in range 0, w as patch size.
We would like to eventually turn this into a Flask application where you either select images from a drop-down or provide a link to an existing image and it will analyze it for you. We would like the multi-stage analysis. Currently we have clone, ELA, PCA. We would like to stage them somehow to provide better results. We would like some sort of testing. So we will eventually need a bunch of images, some that are known to be manipulated and some that are known to be original, legit images from not retracted papers. That will be handy. We could use an overall summary for this chat today. Yep. While it's generating, yeah, just realize if we're doing an image search and we pop the gel array, okay, whatever. No, yep, that's the one. Right, so it's giving all this similar looking images. I assume most humans are nice and they do not manipulate the images, I would imagine. Apologies if this is this should not be copyrighted or anything. Just need the actual thing. Assuming this image is not manipulated, the PCA should have mostly white areas in it. Assuming that's a legit one. Okay, so this is what we had for the known to be manipulated gel array image, and this is the other one. So yes, it's mostly black. There's still some white sections in it, which yeah, which will result potentially in a false positive. Looks like manipulation in there. This wasn't. This is a bit odd. Yeah, that bit there. This one wasn't retracted, was it? Sometimes it's not obvious. I don't know why journals do not make it absolutely obvious if the paper was retracted or not. Looks either like low resolution or yeah, it looks like manipulation there, like a more obvious to naked eye, but well, there is no indication this image was problematic. Yeah, those images, they just have like an artifact the way they were taken. Yeah, it looks like yeah, just quite a bit of artifacts. Just quickly go over Other things, we have this new blog, vision impairment simulator, a neural network training tool. It's not a tool, just an example, simple example. Go check it out. And hopefully there will be many other tools that you will enjoy. And don't forget to provide your feedback. I'll see you in a bit. Bye.